This is video 2 in the lecture on reliability. Now that we understand the mainstream approach to accelerated lifetime testing, let's discuss some caveats. Let's look at that activation energy. The Automotive Electronics Council writes that 0.7 eV is a typical value. Actual values depend on failure mechanism and range from -2 to 1.4 eV. AEC-Q100 applies to chips or integrated circuits. So, let's look at activation energy values for some on-chip failure mechanisms. This is a table of some types of failures that can affect semiconductors. The top few lines are failures related to on-chip transistors. The bottom lines relate to metal traces, which make the connections between the transistors on the chip. Note how most of these values are higher than the 0.7 eV that AEC-Q100 called typical. Corrosion, in contrast, is much less. How do these differences affect the Arrhenius equation? Let's redo the calculation in our example for some different values of EA. And for convenience, also list the results in days. You can see that the impact of the exact choice of EA is significant. An analysis based on 0.7 eV will underestimate the impact of fault mechanisms with a smaller EA and may overestimate the impact of mechanisms with a larger EA. As imperfect as this is the standard industry approach. The key ideas in this last section were that EA equals 0.7 electron volts is a rough assumption, and the Arrhenius equation approach to accelerated lifetime testing is a compromise between rigor and practicality. Next, let's define the term mission profile and design a mission profile for a BMS. Now, let's consider what's unique about a battery management system and compare that to our example system. Our example had this mission profile. Let's take a moment to define the term mission profile. A mission profile is the collection of relevant environmental and functional loads that a component will be exposed to during its use lifetime. In other words, a mission profile is the customer-specific lifetime requirements for a given product, parameters like temperature and duration. Let's spell out what a BMS mission profile might look like. We discussed earlier that the product lifetime in years depends on the application. For a small device like a phone or a toy, the lifetime might be 5 years, and the device might see 4 hours of use per day with an average temperature close to room temperature. With fewer total hours of use than our example, and a lower operating temperature, calculated accelerated lifetime test requirements should be much less than those in the AEC-Q100 example. A car BMS is another story. The longer lifetime and more hours of daily use bump up the operating hours to nearly triple that of the example. However, lithium-ion batteries shouldn't be operated above about 45 degrees centigrade. That said, the temperature of the BMS PCB may be higher than the cell temperature, especially if high balancing currents are used, or if the BMS electronics are co-packaged with other higher power electronics. A solar backup home energy battery may have a 30-year lifetime and operate 16 hours per day, with a total lifetime operation of some 175,000 hours, nearly 15 times longer than our example. Let's take the mission profile values from the previous slide and plug them into the Arrhenius equation to calculate the corresponding bake times for accelerated lifetime testing. It all looks great. All 3 of our BMS applications require less than the standard 40-day bake time. Is that what you expected? In particular, look at the solar backup battery. Its operating lifetime is 15 times longer than the AEC-Q100 example, and yet the accelerated lifetime testing bake time is shorter. Does that make sense? The key is the temperature. If the mission profile average temperature increases, the bake time increases dramatically. For example, look at how the bake time increases with temperature for the solar backup BMS. If our BMS ran at 87 C, the same as in the AEC-Q100 example application, we would need an 850-day bake time to validate our reliability target. That's over 2 years, totally impractical. The value we assume for the mission profile temperature is key to getting valid results from accelerated lifetime testing. The previous calculation assumed a 125 degrees C bake temperature. Not all ASICs are designed to operate at that temperature. Some BMS chips on the market have a max operating temperature of 85 C. If we redo the calculation with an 85 degrees C bake temperature, we find that 2 of these applications require an impractically long bake time for validation. And if you can't validate the reliability of a thing, maybe you should worry about the reliability of that thing. Chips designed for 85C operation may in practice have worse reliability than chips designed for 125C operation. Many techniques for improving reliability and for increasing max operating temperature are the same. Let's consider how we might go about defining a mission profile. First, let's analyze temperatures within the system. Consider a home energy storage for a house. Imagine a battery with 13 or 14 LFP cells in series with a max voltage of around 50 volts. Associated with that, we have a printed circuit board with control electronics. On the PCB, we have a BMS. It includes chips for voltage sensing, battery current sensing, and cell temperature sensing. We also have a microcontroller for state estimation, diagnostics, and safety functions, and some support circuits, for example, to control the battery switch. The system also includes power electronics or inverters to move energy between the 50-volt battery and the home's 120-volt AC. These switching converters are highly efficient but not ideal. They will dissipate some heat. We know that the cells have a max operating temperature of 40 or 45 C. Lithium-ion cells are damaged by higher temperatures. Our ambient temperatures may be similar. In the summer, you might see long stretches of 35 C daytime temperatures in sunny places where solar energy is most reliable and thus appealing, a key target market. Let's consider heat sources on the PCB. In the BMS, the main heat source is balancing. Depending on the choice of balance current, the balancing resistors may dissipate a few watts. However, high balancing currents are usually short in duration. A high current can rebalance the cells quickly. The power electronics may dissipate a lot more, tens or hundreds of watts. Through a combination of thermal design and testing, the engineers will need to characterize the heat increase caused by the electronics. Without actually doing the analysis, let's just assume that the power electronics and their enclosure are designed for a 75 C maximum operating temperature, which allows 35 to 40 C of self-heating above ambient. Estimate the daily operating cycle. Perhaps we charge from solar panels during the day, with the switching converters shuttling more energy as the sun shines more brightly midday. In the evening, we discharge the day's accumulated energy. With a high balancing current, balancing is a small fraction of the day. We might balance at night, when the battery is well rested and not much else is happening. Next, let's get more rigorous on ambient temperature. You might look up ambient temperatures over time for the most challenging climate where you intend the product to perform well. For example, in Phoenix, Arizona, daily temperatures fluctuate like this in mid-July and in mid-December, the hottest and coldest months of the year. We can add the self-heating of our electronics on top of that ambient profile with bumps in temperature due to balancing and the switching converters, and calculate the average temperature on the PCB, average for the whole year. This is our application temperature for the Arrhenius equation. This temperature over time profile constitutes the mission profile needed for designing our reliability tests. In reality, we would also include the maximum operating voltages, since some failure mechanisms are exacerbated by increased voltage. Let's go back to our table and correct our math. Previously, we had 40 C, where now we have a more carefully derived 45C. When we update our calculation, we see that our accelerated lifetime bake will require 43 days. That's close enough to 40 that we can say we're okay. Just be sure to design the PCBs with components rated to 125C, so you can run the accelerated lifetime tests at 125C. Let's consider one last caveat for BMS mission profile. In a BMS, some of the electronics are always connected to the cells. They are always powered. When designing that mission profile, we need to ask, what does it mean to be operating? Does operation mean exposure to voltage or active switching? Arguably, the voltage measurement circuits and switches that are directly connected to the cells are always on. With that assumption, if we update the hours per day to 24, our mission profile changes to one that we may not be able to validate in a 40-day accelerated lifetime bake. This is actually a pretty tricky question. Some aging processes are affected by switching, and some are not. The key ideas in this section were that the mission profile differs across applications. Use duration and average temperature are inputs into the Arrhenius equation. A higher bake temperature reduces test time. A higher mission profile temperature increases test time. A higher bake temperature may require higher temperature components. At this point, let's discuss how reliability testing fits into the overall design and test process. First, let's consider an idealized reliability test flow. We design and build the first version and test the basic functions. Then, test the population. It's often too time-consuming to test multiple units manually, so we need to design and build an automated tester. We bake this population of tested units to emulate aging. In standard accelerated lifetime testing, the longest bake is about 40 days. Then, we retest the baked units. We look for failures and for large shifts in performance. With these learnings, we build the next version, addressing any failures with design changes. And then, we repeat the process of testing, baking, retesting, and evaluating, repeating until the baking results in 0 failures. This is a very time-consuming process, so in practice, a few shortcuts are common. The first time through this process, we might test only a partial set of functions. For example, if the automated tester is not yet fully programmed and the testing is done manually. We might test only a small number of units. And we might pause baking to check for failures so we can start debugging and addressing any early failures before the full 40 days. The whole process, when done with the target number of units and a complete test program, is called qualification, or in shorthand, qual. The abbreviated process is referred to as pre-qual. Last but not least, reliability should be a focus during design, not an afterthought in response to reliability test failures. You might use AEC-Q100 and AEC-Q200 components in non-automotive, long-life applications, knowing that they undergo more thorough qualification and manufacturing quality practices than standard components. Choose higher temperature-rated components, for example, 125C parts for lower temperature but long-life applications. Run a pre-qual early, as soon as possible. Consider self-heating and thermal design early. While the most accurate thermal simulation or thermal test requires a finished design, you might put a large ground plane for heat dissipation beneath your shunt resistor and balancing resistors, or choose a PCB vendor which offers the option of thicker copper should better lateral heat conduction be needed. This completes the lecture on reliability in my Battery Management Systems course. If you liked what you saw and would like to see more, please help this course get seen. Share it with a colleague, share it with a customer, share it with a favorite college professor, and of course, subscribe, like, and comment.